Imagine we have a function like this. This is a power series center A, and it only makes sense or converges inside a certain interval. Then the interval can express as A minus R and A plus R. The interval is determined by the R, and R is radius of convergence. Now we have a question. If I take the derivative or an integral of this series, will it still converge? And if so, can I just differentiate and integrate each term one by one? Well, this theorem will tell us yes, we can, and the radius of convergence stays the same. And first, we talk about differentiation first. To differentiation of functions, we multiply n and power n minus 1, like this. This is 2, then we multiply 2, the powers will become 2 minus 1, and all term will multiply n and powers n plus 1. So this function can also express as this. Then we differentiate each term just like we do for a polynomial, and it still works. So the special place is that the new series still converge on the same interval from A minus R to A plus R. So this is pretty convenient to us. We don't need to recalculate the radius. We can just use differentiation to solve the problems. And now let's move to the integration. We can integrate functions by divided it by n plus 1. This is 0. This is a constant. We plus a constant to integral function. Then we divide 0 plus 1 for first term, and it will got x minus a powers 0 plus 1. To every term, all will divided n plus 1, and all will powers n plus 1 too. So the integral function can express this as this. And we can find that this is just as same as we integral the power series directly, because when we integral the power series directly, we got that we got this. So we can just integrate a polynomial term by term. The radius of convergence will remain the same as the original radius of convergence, and also as the differentiated one. So let's do a simple question to more realize how it works. The example is we need to find the power series for this function, and its radius and find its radius of convergence. So first we can observe this function. We found that it is similar to function like this. So we write it and turn it to the power series type. Because power series have a standard like minus x, so we get negative x power n. After we got this equation, we've observed the question's function and our equation. We found that when we differentiate our equation, the left hand side will become like the left hand side will become like this, and it just the negative of our problem is it just multiply a negative to our question's function. So next we differentiate the right hand side to find that the power series type can express as this, and we differentiate it so we get this. To this step, we are not finished it at all. We need a final step is to multiply -1 because the problem's function is positive. So after we multiply -1 to both sides, we got that 1 plus x is equal to n plus 1 and x n minus 1. So we can use the original function's radius of convergence to find the new after differentiate its radius of function, because the radius function will still same after we differentiate a power series. So we know that power series has the rule is when x when x little than or smaller than 1. So our equation is when -x smaller than 1. And the radius of convergence have the definition as if x minus a is smaller than r, then the r will be called radius of convergence. So by this equation, equation. By this, we can find that the original radius of convergence is 1 because its x is in this. So after differentiate it, we know that the power series radius of convergence will be the same. So this problem, we found that the power series for these functions is this. The power series of this function is like this, and its radius of convergence is 1. Thanks for your listening.